Now recall that a single variable function defines what's called a change of variable or a change of coordinates. So as a very simple example, let's take this function x equals e to the u. Now if I take the domain here to be closed interval 0 to 1, this function or mapping takes those points in the interval and takes them to a new set of points on the real line. If this value of u is equal to 0, that means x will be e to the 0, which is 1. So this one endpoint will get mapped to this value here of 1. And if u is equal to 1, that means x is e to the 1, which is e. This other endpoint gets mapped to this value e. If we were to take every single point in that first interval, we could map it to every single point in that second interval. So what's happened is that function has mapped this interval 0 to 1 into the interval 1 to e. Now what we're noticing here is that the variable u has changed and turned into x. The length of this interval was 1, but the length of this new interval is e minus 1. So there has been a length distortion due to this transformation. All of these ideas are quite simple when we have a single variable, but they generalize very nicely to multiple variables. So we're going to start by considering a generalization of this idea to R2. Now, the notation we're going to use is the letter T for transformation from R2 into itself. So we'll start in what we'll call the UV plane, and we'll take some point U and V as inputs, and we will create new outputs, X and Y, but they will be functions of the two input variables. So we'll have X of U and V and Y of U and V. We are transforming this point UV into some new point X and Y according to this rule. Now, we are going to be interested in elementary regions. So we'll call this region here D star. Now, remember that elementary regions are closed and they are bounded by continuous functions. Now, it doesn't matter if we choose to write them as functions of x or functions of y. We are going to see whether or not this will map into some other elementary region D. And we will say that D is the image of this D star under the transformation T. So sometimes we'll write the notation given by this representation. So as a very simple example, we will have T of U and V is 2U plus 1 and 3V plus 2. So this will be our new X coordinate and this will be our new Y coordinate. We are going to take D star to be the unit square here. So this will be our U value and this will be our V value. What does this transform into under our transformation? Will certainly help to draw a picture here. So we'll have intercepts there. We'll start by seeing how individual sides map to other individual sides. So here on side 1, we have the value of u is 0, and then the value of v is going to vary from 0 to 1. How does that get mapped into the xy plane according to this rule? So by the transformation t, if u is equal to 0, that means x will be 2 times 0 plus 1, which is 1. V is trapped between 0 and 1. 3v is trapped between 0 and 3. 3v plus 2 is trapped between 2 and 5. Or y is going to be trapped between 2 and 5. The first side will get mapped to this area over here. Now we're just going to repeat this process. And on the second side, what we have is that v is 0 and u varies between 0 and 1. Y is 3 times v plus 2. Which just ends up giving us a 2. U is between 0 and 1. 2u is between 0 and 2. 2u plus 1 is between 1 and 3, or x is between 1 and 3. Side 2 maps over here. On side 3, u is equal to 1. V varies from 0 to 1. This tells us that x is going to be 3 and y is going to vary from 2 to 5 by using the same reasoning that we talked about above. On the fourth side, which will be up here, v is equal to 1 and u varies between 0 and 1. the value of y is equal to 5, and x would vary from 1 to 3. So you can see that we have transformed the boundaries of this one area to the other area. Now, if we sat and took all the individual points in here, we could show that they would map to all the individual points in there. Now, what's happened here is that we've got a square that has an area of 1. Mapping has now turned this into a rectangle, and the area of this rectangle now is 6. So t distorted the area by a factor of 6. Now, this type of transformation was special. This is an affine transformation. Now, an affine transformation in R2 looks something like this. We'll always be able to write x as some bunch of u, some constant bunch of v plus a constant k1. Y is some other bunch of u, some other constant bunch of v, and some other constant k2. We will call this a linear transformation if k1 and k2 are equal to 0. So we'll write this in column vector form. We're used to writing vectors here horizontally, but there's no reason why we can't write them vertically as the inputs of a column. We'll group these two terms as another vector, and then we'll have the last two constants there. Now, there's a special definition in linear algebra or in matrix algebra that allows you to split this up into what's called a matrix. So it's a box that holds some numbers multiplied by a different vector, and that vector here would be u and v. Our output vector is this vector x. It will be a matrix times this input vector, and then there'll be some other additional vector here. This is the form of an affine transformation. Now, again, if it's a linear transformation, that b term would be equal to 0. Now, from linear algebra, if we have an affine transformation with a determinant of the matrix A not being equal to 0, remember that the determinant of a 2 by 2 matrix is simply this product of diagonal entries that are then subtracted. So if we follow linear algebra ideas, we can show that if we have an affine transformation with a determinant that is non-zero, then that transformation turns out to be invertible. If there's a transformation that takes you from the UV plane, there's a way to reverse it. But in our case, what's most important is that if we have a non-zero determinant, that this transformation will map parallelograms to other parallelograms and vice versa. So if you start with a parallelogram, you will turn it into one. And conversely, if you have an image that's a parallelogram, it must have come from an original parallelogram. The area distortion factor of this transformation T turns out to work like this. The area of the new parallelogram or the new region is the absolute value of the determinant of the matrix used times the old. Now, in the example that we were working with here, 2u plus 1, y is 3v plus 2. We could have written it in this form, 2, 0, 0, 3, uv, 1, and 2. Here's our matrix A, and we can see that the determinant of this matrix is 2 times 3, which is 6. That's precisely the area distortion factor. Now, of course, not all transformations have to be affine. And the transformations that are not affine, we are going to call them non-linear. And the most common one that we will use is the following, where if we take r and theta, we map them into r cos theta and r sine theta. This is our x value, this is our y value. This is the polar coordinate transformation where we take r and theta values and turn them into x and y values. Now let's start with a parallelogram in this input space. So we'll take r values to go from 1/2 to 1, and we'll take theta values that go from 0 to pi. In this space, what we will have is a rectangle. And that's the shape of our rectangle. What we're interested in is seeing how this rectangle maps when we apply this transformation. And on side 1, the radius is exactly equal to 1/2. Our angle goes between 0 and pi. So if we were to map this into the xy plane, we'll observe the following. X would be 1/2 cos theta, y would be 1/2 sine theta. And these are just points on the circle that has a radius of 1/2. So if we start there, x values will go from negative 1/2 to positive 1/2. Our y values will go from 0 to 1/2. There is our mapping of our region 1. Boundary 2 has theta is 0, but the radial values go from 1/2 to 1. And in this case, if theta is 0, that means x is equal to r and y is equal to 0. This turns out to be the image of that part. Along 3, the radius is 1, but the angle varies from 0 to pi. X is cos theta, y is sine theta. And this is going to be the points on a unit circle that have a positive y value. And this will end up being at -1. And finally, if we are on the top region here, what we've got is theta is pi, and our radial values go from 1/2 to 1. So this ends up producing x is -r, y is 0, and we will fill in this boundary right there. So there is 4. All of these points in our nice rectangle, they didn't stay as a nice linear box. What happened is that they got bent. So the points in this region D star were bent under this non-linear transformation, and they produce a new region D. Now finally, transformations can go from R3 into R3, or even Rn into Rn. There's no reason for us to stop at R2. We just do so because it's convenient for visualization. The simplest example that we can talk about here is the cylindrical coordinate conversions, where we take a point in cylindrical coordinates and we turn it into some x, y, z. Those are our Cartesian coordinates. So if we wanted to take a box that was an extension of the one we talked about in the previous example, except now we add that z coordinate. So we are basically taking a box that looks like this, our theta and z. We go from 1/2 to 1 up to pi. We'd have some box, and then we would extend it up into that z direction. So there is our box D star. You can show that under this transformation, we would end up getting something very similar to what we saw in the polar example. We'd have a 1/2 to 1. All we would do would be to extend this vertically. And so the box is bent into this horseshoe shape.